Rightio, and now we're going to have a go at doing a 3 by 3 one. So it's exactly the same, it's just seeing the determinant of the matrix, making the leading diagonals take away lambda. So write down that top left to bottom right, you have to subtract lambda from each point, make it equal to 0. Okay, and then we're just going to find the determinant of this. The determinant of a 3 by 3 matrix, hopefully you remember, is just going to expand by the first row, so it's the first element times the determinant of this piece here, which is that one times that one, minus that one times that one. And then negative, because of the old, remember the old plus minus plus thing, the place signs. So minus this number times the determinant of what's left, which is that one times that one, minus that one times that one, plus negative 2, lots of 10, take away 2 lots of 4 minus lambda. And all of that lot equals 0. So all we have to do is solve this equation to make it equal to 0. So what have we got? Expanding some brackets, we've got 2 minus lambda, and then in this lot we've got 4 times negative 5 is 20, plus 20 goes away, that's handy, plus 5y minus 4y is just y, and then plus y squared. And then for this lot we've got 3 lots of, what have we got here? We've got minus lambda, and negative 5 plus 4 is negative 1. And then we've got 2 lots of 10 take away 8 is 2, plus 2 lambda equals 0. Expanding this bracket out gives us negative lambda cubed, plus 2 lambda squared minus 1 lambda squared is just plus lambda squared, plus 2 lambda. And then we've got plus 3 lambda plus 3, and then we've got minus 4 lambda minus 4 equals 0. Collecting like terms gives us negative lambda cubed. That's the only lambda squared we've got. Straight lambda terms, we've got 2 and 3 is 5, take away 4 is 1, and then we've got 3 take away 4 is minus 1. Okay, so that's the cubic that we have to solve. So hopefully you've got some experience of solving a cubic, but basically the way to do it is to figure out one solution. So this looks really promising for 1. So if lambda is equal to 1, you'd have take away 1 plus 1 plus 1, take away 1 is 0. So there's definitely got a solution at lambda equals 1, which means we know that lambda minus 1 is a factor, and then we're going to be left with a quadratic bit, which has to be minus lambda squared for that bit, has to be plus 1 on the end of it. Okay, so lambda times minus lambda squared is the only way you're going to get a lambda cubed, and then we're going to get a negative 1 here is negative 1 times 1. So let's check the lambda squareds. We've got plus 1 lambda squared plus another lambda squared makes 2 lambda squared, but we only want 1 of them. So we've got to lose another lambda, and that should work out for the straight lambda. So we've got plus lambda. Nope, I've managed to do something wrong here. What's gone wrong? Solution at lambda equals 1. It's always embarrassing when this happens. So, oh, yeah, that's right, lambda equals 1, so minus lambda plus 1 plus lambda squared. Oh, what am I doing here? Okay, sorry, just been an idiot. Checking the plus lambdas, we go negative 1 times negative lambda is plus lambda squared, and it works out. So if we expand that, we get back to that. And then this piece we can now factorise, lambda minus 1. This thing will factorise into minus lambda plus 1, and lambda plus 1 equals 0. And so the solutions are lambda equals 1 from that one, lambda equals 1 from that one, or negative 1 from that one. So we have 3 eigenvalues, with 2 of which are repeated, at negative 1 and 1 with a a repeated root in that answer. So with 3 by 3 matrix, you're going to end up with 3 eigenvalues, and you do need to be able to sort out what's going on with a cubic. You need to be able to solve a cubic, so you may want to review how to go about solving a cubic if you need to.